Welcome to another class on bending stress in beams. And before I move on, I want to tell you, for better understanding, please watch my video lectures on bending stress in beams one by one in sequence. Now let us solve this problem on your screen. A simple beam of length 5 meter carries two types of loads: a UDL 6 kN acting over the entire span, a point load of 2 kN at a distance of 2 meter from the left support. The cross section is shown in figure 2. This is the figure 2. Calculate the maximum bending stress at a distance of 3.5 meters from left support. All we have to find, we have to calculate the maximum bending stress, sigma max, at 3.5 meters. Okay, 3.5 meter from left. We have to calculate this. Now we know the bending stress equation is m by I is equal to E by R is equal to sigma by Y. Okay, now from here we can write sigma by Y is equal to m by I. Okay, from here we can find sigma as my divided by I, right? Now this sigma is the bending stress, m is the moment at the section, y it is the depth of neutral axis, y is the depth of neutral axis at which we want to find the bending stress, and I is the moment of inertia, area moment of inertia. Okay, now but we don't have to find the bending stress, we have to find basically the maximum bending stress. Okay, sigma max. Okay, now as you can see here, sigma max bending stress will be maximum when the moment is maximum and y is maximum, right? Because I is the moment of inertia of this section, I is a constant. Okay, now sigma is directly proportional to the moment and sigma is directly proportional to y, right? But here is a condition, we have to find sigma max at 3.5 meters from the left. Now in this diagram you can see, if we draw the bending moment diagram of this beam, you will see the bending moment varies. Okay, bending moment is not same at every point of this beam, right? But here we have to find the bending stress at 3.5 meter from left side, right? Means we have to find bending stress at a fixed distance from A, right? Now when we fix a distance, let's say this is 3 meters, at this point this is 3 meters. Okay, now here will be a fixed bending moment, right? It means m is also constant. Okay, because we have the condition here 3.5 meters from the left. If it was not 3.5 meters from the left, okay, if it was just asked to find the maximum bending stress, then we would find the maximum bending moment in this beam, right? But because we have this condition, the m will be constant, because at a distance of 3.5 meters, okay, 3.5 meters from the left, the bending moment will be constant, and we have to find that bending moment. Okay, so m is constant too. Now what is remaining is y. Okay, sigma is directly proportional to y. It means when the y is max, okay, sigma will be max too. Okay, so our formula is this: sigma max is equal to m y max by I. Okay, so we don't have to find the just the y, we have to find the y max. Okay, we will see what this is basically in the diagram. When we will solve this problem, you will understand all of these terms very well. Okay, very clear. Now let's first begin with finding the moment. Okay, we have to find moment, we have to find y max, we have to find I. Okay, just let me just write these things here. We have to find the moment, we have to find the y max, right? And we also have to find I, right? We have to find these three terms, then we will be able to find the maximum bending stress at 3.5 meters from left, right? Let me also write this equation here. sigma max is equal to m multiplied by y max divided by I, where I is the moment of inertia. Okay, so let me erase all of that. Okay, now let's first find moment. Okay, now to find the moment we have to first find these support reactions Ra and Rc. Okay, let me draw a support reaction here. Let us say here is a reaction, this is Ra, and let's say here is a reaction, this is Rc. Okay, reaction at C. Now let us assume this to be x-axis and this to be y-axis. Now we know summation of f of y is equal to 0, right? It means Ra plus Rc minus 2 minus 6 multiplied by 5 is equal to 0, right? Now I have assumed the upward reactions are positive and the downward are negative. That's why I write Ra plus Rc. Now there is 2 downwards, I write minus 2, and there is a UDL of 6 kilonewton per meter. So the total load due to this UDL is 6 multiplied by total length. Total length is 5. So it is 6 multiplied by 5. That's what I have written here. So from here we will get Ra plus Rc is equal to, now 6 5 is 30 and plus 2 is 32, right? Let us call this as equation number 1. Okay, so we have this reaction. Now let's apply the moment at C equal to 0. Okay, summation of moment at C is equal to 0. So what do we get? Ra multiplied by 5, right? Because Ra is 5 meters away from C point. Ra multiplied by 5. This is clockwise movement, right? And I write the clockwise movement as positive, and I will write the anti-clockwise movements as negative. Okay, now there is 2 kilonewton load which is at a distance of, from here to here is 2, total is 5, so from here to here is 3 meters, right? So minus 2 kilonewton multiplied by 3 meters. Now there is UDL minus 6 multiplied by the, how much is the total load of UDL? 6 multiplied by 5, right? Because 5 is the total length. Now we can assume the UDL is acting at the center of this beam, right? Whose magnitude is 6 multiplied by 5. And how far is it from C? From here to here it is, total is 5, total is 5 meters. So from here is 5 by 2, right? 5 divided by 2 is from here to here. So we'll write here 5 by 2 is equal 0. Okay, now again, if you don't know how to find the reactions, how to apply this these equilibrium equations, please watch my video lecture on how to draw shear force diagram and bending moment diagram of beams. You will understand this well, and I don't think there you will be, it will be very difficult for you right now to understand, because this is really, because these are really simple things. Now 5 Ra minus 3 2 is 6 minus, now here 2 ones are 2, 2 threes are 6, right? Now 5 5 is 25 and 25 multiplied by 3 is 75 is equal to 0. So we will get 5 Ra is equal to 6 plus 75. How much is that? 75 plus 6 is 81, right? So we got this to be 81. So from here we will find reaction at A is 81 divided by 5, which is equal to 16.2 kilonewton. Okay, now we found reaction at A is 16.2, right? Now this is 16.2 kilonewton, right? Now because this is 16.2 kilonewton plus RC is equal 32, from this equation, right, we can find RC is equal to 32 minus 16.2, which is equal to 15.8 kilonewton. Okay, now we found this, it is 16.2 kilonewton, and reaction at C is 15.8 kilonewton. Okay, so let me rub all of this. And before I move on, I want to tell you, if you want to download the PDF of this lecture, it is in the description. You can first watch this video lecture very carefully, and when you completely understand everything, then you can download the PDF. Don't worry about writing, just try to understand now. Anyways, now we know RA 16.2 kilonewton and RC is 15.8 kilonewton. Now what we wanted to find, we wanted to first find M, right? But where we have to find moment at 3.5, because it is saying calculate the bending stress at a distance of 3.5 meters from the left. Okay, so let's assume this XX is the section at a distance of 3.5 meters from the left, from A. Okay, so let's find moment at this point. So moment M at X is how much? First is reaction multiplied by distance up to X. X is 3.5, right? RA multiplied by 3.5, right? Because load multiplied by distance gives the moment. So reaction is 16.2 multiplied by distance is 3.5, right? So it was due to RA. Now here is a point load 2 kilonewton. Because it's acting downwards, it will exert an anti-clockwise moment, so I will use negative here. Okay, now how far is 2 from this X section? Now see, from here to here is 3.5, from here to here is 2 meter, right? This is 2 meter, and from here to here is 3.5. So how much is here? It is 3.5 minus 2, which is 1.5, right? Now first let me write the load. Load is 2 kilonewton multiplied by, and the distance between the load and the section is 1.5 meter, right? Okay, so we found due to this, and we also found due to this. Now let's find the moment at XX section due to this UDL, right? Again, the UDL will exert an anti-clockwise moment, right? So it is minus the per unit load is 6 kilonewton per meter, 6 kilonewton per meter multiplied by how much is the load from A to X. 3.5 is the length and 6 is per unit, so 6 multiplied by 3.5, right? 6 multiplied by 3.5, it is the load from A to XX section, right? Now we found the load, now we have to find the distance multiplied by. Now let's assume this UDL is acting at the center of this 3.5. Okay, now when it is acting at the center of 3.5, then from this point up to this point is going to be half of 3.5. Okay, 3.5 divided by 2. Okay, now when you will solve all of this, you will get moment to be 16.95 kilonewton meter. Okay, so we found the moment 16.95 kilonewton meter, right? So let me rub all of this. Now we found the moment. Okay, now the next term we need to find is y max and I. So let's first find I. Okay, I is the moment of inertia of this complex section. Okay, basically it is a section. Okay, all of this is solid. Okay, and this is a circle cut out from this lamina. Okay, this is a hollow circle. This is like a thin sheet, and in from this a circle is cut out, right? So we have to find the moment of inertia of the this whole lamina with a hole. Okay, But to find the moment of inertia of this section, we need to know the neutral axis first. Okay, the neutral axis. We have to know the neutral axis. Neutral axis. Okay, it's also denoted by NA. Okay, if we draw a line somewhere like this, and NA means neutral axis. Now, what is neutral axis? Neutral axis is an axis, okay, where bending stress is zero. Okay, and it is found the bending stress is zero at the center of gravity. Okay, center of gravity or centroid. Okay, they are the same thing. It means we will find the location of center of gravity. Okay, at that location, that will be the location of neutral axis. So we found the neutral axis. So let's first find the center of gravity of this section. So let me draw this section here. Now you can see this lamina with a hole. We can divide this into two simple parts. Okay, let the whole rectangle, we will assume the whole rectangle with no hole. Okay, be element 1. Now this element 1 is the whole rectangle, assuming there is no hole. Okay, and let us assume this hole to be element 2. Okay, and let us choose this as our x axis of reference. Okay, this is the x axis. About this we will find the center of gravity of this part. Okay, now let the center of gravity be denoted by y bar. Okay, y bar is the distance of center of gravity of this hole from x axis. Okay, we know the formula, summation of ai yi whole divided by summation of ai. Now we only have two elements. Okay, so this will reduce into a1 y1 minus a2 y2 divided by a1 minus a2. Okay, so this, all of this, it will reduce into a1 y1 minus a2 y2 whole divided by a1 minus a2. Now why use the minus, why I didn't use the plus here? Because this is not a material. Okay, it is a hole. That's why I'm using negative here. Now a1 is the area of this rectangle, assuming there is no hole. Okay, so what will be the value of a1? A1 is, the width is 250 and the depth is 400, right? So how much is going to be a1? A1 is 400 multiplied by 250. How much is it? A1 is 100,000 millimeter square. Okay, now y1 is the depth of center of gravity of this rectangle, assuming there is no hole from the x-axis. Okay, now you can see, if you assume, let me draw it here, because element 1 is without the hole. Okay, now the total is 400, right? This is 400 mm, and we want to find, this is x-axis, we want to find the distance of center of gravity of this rectangle from the x-axis. Okay, because rectangles, they are symmetric, so the center of gravity will be in the midpoint. Okay, because it is symmetric. If I draw a line like this, from this is the center of gravity. Now from here to here it is y1, right? Now from here to here it is 400. So from midpoint to up to this point is half of 400, right? Which is 400 divided by 2 is 200 mm, right? So y1 is 200 mm. Again, if you have difficulty in understanding this, please watch my video lecture on center of gravity and moment of inertia. You will understand where did I get this formula very well. Now again, here a1 is 100,000 millimeter square. Okay, we are done with element 1. Now let's talk about element 2. Okay, so let me draw the element. This is our element 2, right? A2 is what? A2 is the area of this element. Okay, we know area of a circle. If the diameter is given, the diameter is here 150 mm, right? This is 150 mm. This is the diameter. So what is the area? A2 is going to be pi by 4 d square. Dia is 150, right? 150 square. How much is it? 17662.5 millimeter square. Okay, so this is 17662.5 millimeter square. Okay, now y2 is what? Y2 is the distance of center of gravity of this hollow circle from the x-axis. Okay, now see, from the top to the center here, okay, is 100. Okay, and the total is 400. So how much is going to be from here to here? 400 minus 100 is 300, right? 300 millimeter, right? This is y2. Okay, this is 300 mm, and a2 is 17662.5 millimeter square. Okay, now we have all of this. We have a1 y1 a2 y2 a1 y1. We have all of the value. When we solve this equation, we will get y bar to be 178.55 millimeter from x-axis. Okay, so let me show it in a clean diagram. Okay, now this is the distance of the center of gravity of the whole rectangle section with a hole from x-axis. So this is also the neutral axis. Okay, location of neutral axis. So if I erase all of this, now let's assume this line to be the neutral axis. Okay, from here up to this point is depth of neutral axis, right, which is 178.55. Okay, this is NA, neutral axis. Okay, now I is the moment of inertia about this neutral axis. Okay, I can also write it as INA. Okay, INA, this is the moment of inertia about the neutral axis. Now how are we going to find the moment of inertia of this section about this neutral axis? How is it possible? Now almost every student or even the teachers, they know the formula of finding the moment of inertia of the simple objects, symmetric objects about their center of gravity. They know it very well. Okay, for example, I know the moment of inertia of this circle with respect to its center of gravity. I also know the moment of inertia of the whole rectangle without hole about its center of gravity, right? But we don't need this. We don't need the moment of inertia about this, right, center of gravity of the circle. We also don't need the moment of inertia of this rectangle without hole at its center of gravity. We need the moment of inertia of the whole thing about neutral axis. So what we are going to do, we are going to use the theorem of parallel axis. Okay, we'll be using theorem of parallel axis. If you don't, okay, if you don't know about this theorem, please watch my lecture on theorem of parallel axes, and I will also try to explain here. If you are the beginner, I will try to explain it as simple as possible, and still if you didn't understand, please watch that lecture. Now what we are going to do, we are going to first find the moment of inertia with respect to the centroids. Ig means moment of inertia with respect to the center of gravities. We will find this was element 1, right? Element 1 is all the rectangle. Element 1 is all the rectangle without hole, okay? Without hole. And this is element 2. Element 2 is a circle. What we are going to do, we will find the moment of inertia of this whole thing. We are going to find the moment of inertia of element 1. Of course, it is without the circle. About its center of gravity, because that's really easy to find. Let me show it here. I draw this right here, okay? This is 400 mm. Now, where is going to be the centroid? Because it is rectangle, as I have told you already, it will be at the half distance, right? This will be 200 mm and this will be 200 mm, right? We have to find the moment of inertia of this rectangle about this axis passing through G, okay? Now here is 250 mm, okay? Now you should know the formula of finding the moment of inertia of a rectangle about its own center of gravity is Ig is equal to BD cube divided by 12, okay? Now B is 250, this is 250, D is how much? 400, right? The total depth from here to here is 400. This is D and this is B divided by 12. Okay, when you solve this, you will get Ig to be 1.33 multiplied by 10 to power 9 millimeter power 4. Okay, this is Ig of this. Okay, I'm talking about this. Now this is the moment of inertia about this point, which is at a distance of 200 meter, right? But our neutral axis is at a distance of only how much? Y bar, which is 178.55 millimeter from x-axis. But we found the moment of inertia at 200 mm from this, right? Because it is 178.55 mm, which is less than 200. So the our neutral axis is somehow here, right? We found about this, right? This was Ig, right? We found the moment of inertia about Ig, right? But we need this one. This is neutral axis. Na, okay, this is neutral axis. Now how much is the distance between these two axes? Now see, from here to here is 200, right? And from here to neutral axis is how much? From here to neutral axis is y bar, which is 178.5, right? 178.55 millimeters. Now from here to here is 200, here to here is 178. So the distance between these two is what? 200 minus 178.55. Okay, when you solve this, you will get this distance. Okay, let me call it as something, let's say it be y1. Okay, this is y1 because this is the element 1. All the rectangle without hole is element 1. So y1 is 200 minus 178.55, which is going to be 21.45. This is y1 is 21.45. Okay, let me write here y1 is equal to 21.45 millimeters. Means from here to here is y1, okay, which is 21.45. Now according to the theorem of parallel axes, moment of inertia about this neutral axis, okay, I and A is equal to moment of inertia about the center of gravity plus area of the whole, okay, let it be a1 is the area of the whole rectangle multiplied by y1 square. Okay, okay, I can remember a1 is, we found the area of the whole before, it is 100 and 3 zeros millimeter square. Now y1 is how much? 21.5, and Ig is this much, right? This is 1.33 multiplied by 10 to the power 3. Okay, now when you put all of these values in your calculator, you will get new moment of inertia about neutral axis to be, you will get this to be 1.38 multiplied by 10 to the power 9 millimeter power 4. Okay, so let me call this as INA as I1, okay, or INA1, because this is element 1. So I will write here I neutral axis of element 1 is 1.38 multiplied by 10 to the power 9 millimeter power 4. Okay, now we found the moment of inertia of element 1. Okay, in the same way we will find the moment of inertia of element 2. Okay, but remember element 2 is a whole. Okay, it is a whole. We will subtract moment of inertia of this 2 about neutral axis from the moment of inertia of element 1. Okay, because this is a whole. Okay, so let me erase all of this first. Now we will find the moment of inertia of this circle about neutral axis, again using theorem of parallel axis. Okay, so let me draw this circle first. Now first of all, we will find the moment of inertia of this circle about its center. Okay, if we assume a line like this passing through the center of axis, and let this call as Ig. Okay, moment of inertia about center of gravity, right? This is G. Then we know moment of inertia of a circle about its own center of gravity or centroid is pi r4 divided by 4. Okay, I remember diameter of this circle is 150 mm, right? So the half of diameter is radius, half of 150 is 75. Okay, so this is 75, this is 75 mm. This is pi is 3.14 approximately multiplied by 75 power 4 divided by 4. When you solve this, you will get Ig equal to 2.5 multiplied by 10 to the power 7 millimeter power 4. Okay, now we know the moment of inertia of this circle about the center of gravity, right? Now we will use the theorem of parallel axis. Okay, we have to find the moment of inertia of this circle about neutral axis. As you can see here, we have to find the moment of inertia of this circle about the neutral axis. Okay, now how far is neutral axis from this center? Okay, see, from bottom up to neutral axis is y bar, which is 178.55. It means from how much is from here up to here neutral axis, total is 400, and from here to here is 178.55. so how much is from here to here? It is 400 minus 178.55, right? But we have to find the distance from the center of gravity of this circle. From here to here is 100, so from here up to here is what? Let us call this as y2. Okay, let me call this as y2. So y2 is going to be 400 minus 178.55 minus 100, right? How much is it? It is 121.45 mm, right? Okay, now the y2 is 121.45. Let's keep it here. Okay, somewhere here is the neutral axis, right? Neutral axis, and from here up to here is y2, right? It is 121.45 millimeters, right? Now we can apply the theorem of parallel axis to find the moment of inertia of this circle about the neutral axis, it is going to be I neutral axis, let me call it as 2, okay, because circle is element 2. It is going to be moment of inertia Ig plus ay2 square, okay, or let me call this as a2, where a2 is the area of this circle, okay. Now Ig is how much? 2.5 multiplied by 10 to the power 7. A2 is area of this circle. We know area of a circle is pi by 4 d square. Diameter is 150, right? 150 square. How much is it going to be? 17662.5 mm, okay. Now this is A2, 17662.5 millimeter square, right? Now Y2 we know this is 121.45, and this is the Ig, which is 2.5 multiplied by 10 power 7 millimeter power 4, okay. Now when you solve all of this, you will get INA 2 is equal to 2.85 multiplied by 10 to power 8 millimeter 4, okay. So let me rub all of this first. So we get I neutral axis of second 2.85 multiplied by 10 to power 8 millimeter power 4, okay. Now we know the moment of inertia of the rectangle element 1 about neutral axis, which is this. We also know the moment of inertia of element 2 about neutral axis, which is this. Now because element 1 is the rectangle without hole, which is the real material, and 2 is not a material, 2 is a hole, so the net moment of inertia of the whole section including the hole about neutral axis is, that is denoted by I, okay, or I neutral axis. It is going to be I neutral axis of first minus I neutral axis of second. That is moment of inertia of the whole section about neutral axis is moment of inertia of element 1 about neutral axis minus moment of inertia of element 2 about neutral axis. Keep in mind, if 2 was not about neutral axis, if 2 was about its own axis and moment of inertia of 1 was about its own axis, then they would not subtract, because 2 and 1, the moment of inertia of both 2 and 1 is are about neutral axis, okay. That's why they can be subtracted, because they have a common axis. Now you know INA1 is this and INA2 is this. When you solve, you will get INA to be 1.095 multiplied by 10 to the power 9 millimeter 4, okay. So now we also get moment of inertia about the neutral axis to be 1.095 multiplied by 10 to the power 9 millimeter 4, right. So let me rub all of this first. Okay, now we know the moment of inertia. Now we know the moment. We know the moment of inertia about neutral axis. We know this m. We know INA. Now we just need y max. Okay, the moment we get y max, we can find the bending stress. Now, how to find the y max? Now see, y max, right? It's saying max. Okay, max. Whenever you see max, it means extreme fibers. What? Extreme fibers. See, this is the section, right? It have fibers here, it have also fiber here, it have also fiber here, all of in all of the area, and it also have fibers at the edges, right? This fiber and this fiber, okay, we call them as fibers. Now extreme fibers are this, okay, this is the extreme fiber, and also extreme fiber is this. These two are the extreme fibers. But now we have to find what? We have to find the maximum bending stress. It will be maximum only when y max is maximum, right? That's the reason we write max. Now, where will be y max? Will it be here or will it be here? Right? Now, y max is what? It is distance from neutral axis, right? It is distance from neutral axis to the extreme fiber. Extreme fiber. Okay, distance from neutral axis to the extreme fiber. It means y max can be from here up to here, right? Because this is neutral axis, or it can be from here to here. Now why do you think y is going to be max? See, from here to here the distance is 178.5, right? From here to here, it means the distance of lower. Okay, by the way, as you can see in the diagram, this beam will bend like this. Okay, it means the upper part of the section is in compression and the lower part is in tension. Okay, basically this is a neutral axis. All of the section above neutral axis will be in compression. Okay, but that's it will compress, and all of the section below neutral axis will be in tension. Okay, so this is y max in compression and this is y max in tension. Okay, now which is exactly y max? Okay, now from here to here is 178.85, but how much is from neutral axis to this compression fiber or top fiber? It is 400 minus 178.55. Okay, so we can write y max to be 400 minus 178.55. Okay, how much is it? It is 221.45 millimeter. Okay, this is our y max. So we also found the y max, 221.45 millimeters. Now we know all of these terms, so we can find the maximum bending stress at a distance of 3.5 meter from the left side. So when you put, so let me first erase all of this. And yes, let me remind you, the PDF of this video lecture is in the description. Okay, you can download it from there. So sigma max is going to be m y max by moment of inertia about neutral axis, right? It is 16.95 multiplied by 221.45 divided by 1.095 multiplied by 10 to power 9. Okay, when you solve all of this, you will get the bending stress to be 3.43 Newton per meter square approximately. Okay, so here we find the bending stress in this simply supported beam. Okay, and that's it. Again, the PDF is in the description. If you need help in any problems, please contact me. I can help in strength of material problems in almost all the topics. And that's it for today. I hope you enjoy. If you like, please give me a thumbs up and also share it with your friends who need who are also studying the strength of materials. Thank you.